Yeah, so attention in language modeling. So remember when we described this recurrent neural networks, we talked about this sequence to sequence models, and typically these are used. So input is a sequence of any length and output is a sequence of a different length. It need not be the same length, it could be the same length, it could also be a different length. And that's a general architecture that you have RNNs, and you can use LSTMs or GRUs and anything here. So this is basically a single unit, and you can use simple RNNs, you can do multi-level RNNs, you could do LSTMs, so any unit you could use here. But this is just showing you how they are connected in the time. Okay, so let's look at it more, more carefully. Let's say I want to do a machine translation. I got an English sentence, and I want to translate it into a German sentence, I believe. I don't know Germany, so we'll have to just guess it together. So I ate an apple. So it has 1, 2, 3, 4 words, but the translation has 5 words. Okay, and here we will look at this I is mapped to this ICH here. So if I can just label as 1, 2, 3, 4. So this is ICH. 8 is sort of mapped to this and also to this word. And an is mapped to this word. And finally apple is mapped to this word. Okay. So that's how it is mapped. Now, how do we actually translate this? So now we can do a simple RNN. So remember, in simple RNN, you have the input, you give some outputs, right? At every step. So size of output is same as size of input, and that doesn't work because in this case, my size of output could be larger. And more importantly, other issue is that to output maybe this word, I may have to go input which is beyond the second or third word, right? You might have to look at a longer sentences. So maybe what you could do is delay the sequence. So you have the input sequence here, and instead of outputting immediately, you give some delay and then you start outputting. But this also has a problem. We don't know how much to delay because you might require the first word in your output sentence may be related to the last word in your input sentence. So we don't know how much to delay. So, and also we don't know when to start transmitting, right? So when to start outputting, because you have to have enough context to be able to do that. So maybe we introduce a special marker called the end of the sentence, or the period marker, right? The full stop. And only when the input sentence finishes, we start outputting. Right? So in that case, so I ate an apple, and there will be an end of sentence marker, and the moment this marker comes, then you start outputting, from here onwards. Right? So this is what is called a conventional encoder-decoder architecture. So you have encoder, it processes the full sentence, and while it's processing, there are the hidden states, H1, H2, and so on, H4. And from the final hidden state, you get a context which is called C, which you can label as C. And now from this context, you create the hidden states of decoders. And then, the decoder is very similar to the RNN architecture, depending upon the hidden state and the previous output. You get to the next hidden state and the next output. Right? So this is pictorially represented here. So for example, if you look at this output is dependent on this hidden state, which is S3, and this hidden state is dependent on the previous hidden state and the previous output, which is given as an input to this hidden state. Right? So that's a typical encoder-decoder architecture. And here, we don't have to do RNNs. You can do LSTMs, you can do all complicated, architectures that have been designed. So in this setup, and you can do multi-layer as well. So instead of S1, you would have multiple layers with multiple states, and then each layer feeding to the next layer in the next time state. Okay. So now, what is the problem for this? All input information. Okay. So should we write down the equations, or you can do that for simple RNNs, the encoder-decoder equations? Maybe I'll give it as a homework, ungraded homework. Anybody is not comfortable with this? Okay, so I take it as a yes. I take it silent. I'll interpret the silence to my advantage. Okay. Now, the problem with this method is that all the input information is encoded in the final hidden state or the final context. So, if my input sentence is very, very long, then I have to put a lot of information in the context vector, and my context vector is a fixed size. Even the hidden states are a fixed size. So either I increase the size, but even if I increase the size of that context, which makes the model difficult to train, but still, the sequence length could be even larger, could become very large. So that's one problem. The second problem is in the decoder, this thing is propagated, stage-wise, one to next, and so on. So if I look at the state here, the first state, I got the complete context of the input sentence. But if I go to the next state, then I've already looked at my own output, and based on that I've modified my context. So by the time I come to the last context, I've already diluted the information that I had stored in the input sentence context. So this last word may not be able to, or the second last word may not be able to represent the input sentence very accurately, because I've already passed so many steps and I've already diluted my context. So that's the other problem, that information is propagated by the state recurrence, and this information gets diluted as we do more and more steps of decoding. And the earlier decoder state is close to the context, and later decoder states depend on themselves, and therefore we can lose the information. Okay? So how do we fix this problem? This problem is easy to fix. What I can do is, in my decoder, in addition to passing the context and generating the states as I'm decoding, I can also keep the context and pass it to the decoder separately. So then I'll have two sets of weights. This is WSS, and if I label the context as C, then these weights will be WCS, right? So my state would become a function of the previous state times this weight, the context times this weight, and the previous output times, let's say this is output Y, so here I will have WYS. Right? So three sets of matrices of weights that I use to generate the current state. So if I do this, this context information is propagated all the way till the end, and it's available at every step in the decoding process. So that is wonderful, right? So it does not dilute the encoder output. Initial encoder state is separate, and corresponding to that I have a separate set of weights which I can learn. So it solves the one problem of diminishing information or dilution of information along the decoder. But it does not solve the problem of this single vector, because I still have to represent the complete input as a single vector. Right? And that may become a problem something, because this node may be overloaded with the information. One solution is I make the size of this vector bigger, size of these states bigger, but it has its own problems. Okay? So how do I solve this problem? How do I ensure that, just by using a small context vector, I can still pass on the information from the input to the output? Any ideas?
Just like you did with the context vector, pass information to every output, but you can also do all the input.
So just like the context vector, I pass. I pass what information to the output, to the decoder?
The context vector.
Context is already passed. The hidden state of the encoders.
Yeah, now you.
But which one? This one, which one? No, but everyone I cannot do, because recurrent neural network is a time series model. So my input length could be arbitrary, right? I could work with any input length. So I could pass 1, I could pass 2 maybe, or I could pass 3, right? But I cannot pass all the lengths. One possible thing that you could possibly imagine doing is, so this is the last context, right? Then you can skip one and pass this one, right? This is, I don't know whether people have tried it or not, but this is something that you could, possibly do. And, some of you who want to, do your projects and all can actually try this idea out later. So So this is the final context. This is h of, let's say this is h. Let's say this is h of tx, which is x is the input and tx is the length of the input. So here you can also do h of tx minus 2. So you have a gap of 2. Then from here you do a gap of 4. H of tx minus 2 minus 4. And then you do another gap of 8. So depending upon your input length, using the log length, so this you propagate to the output, this you propagate to the output, this you propagate. So in some sense, you sort of well, this is not exactly, yeah, so somehow, okay, let me say it differently. So this is not exactly a good, yeah, may not be very good, very this way. So you could possibly build layers on the encoder side, right? So one layer is updating its hidden state at one time step. The higher layer could update its hidden state at every 2 time steps. And then you could build another higher layer which could update its hidden state at every 4 time steps and so on. So the encoder, with just log of the context length, you could encode the entire context information into hierarchy of these windows. And then all of these windows you could possibly pass to the output. I don't know whether it will work or not, but yes, this is definitely one idea that you could think about.
But sir, n is still variable, so log n is also variable, so how do you know how much layers to need?
Yes, but for all practical purposes, log n is less than 32. 2 to the power 32 is huge. Right? So yes, you are right, conceptually, but machine learning is about engineering. So I think with log n we can assume it to be, bounded by a constant. But that's a very good point, yeah. Theoretically, yes, it will not work. Okay. But this is one idea, but this I don't know whether people have tried it or not. But what else can we do? So let's build upon the previous idea. You're saying that you pass the context. But the thing is, I cannot pass all the context separately. So can I somehow combine the context and pass it? How?
You can pass the first, like, because you want to predict the first word in the output sequence, you pass the hidden state of first word.
Hidden state of the first word. Okay, wonderful. Very good idea. Excellent. Okay, so let's see. Let me... Okay. So, you are saying that, okay, yeah. Since we want to predict the first word in the first step, maybe we'll pass the first, hidden state to the first word, right? Okay. So, what I do is, I look at the first hidden state and give it here. Now I look at the second hidden state and give it here. And look at third hidden state and give it here, and so on. Right? Good, so as I'm translating, I'm getting more information about it. But then what can go wrong with this?
The output sequence is larger than the...
Output sequence can be of different length, even if they are of the same length. If you look at this example, that, there may not be a one-to-one direct correspondence between the first word of the input and the first word of the output. So I have to shuffle it somehow. Right? And I have to figure out what is the right word to transmit. Right? So that's the key problem. That is the key problem that attention solves. I need to give attention to a specific word in the input given that I am a particular stage in the output. And how do I do that? So one idea that, that they are giving out is I look at all these states and I just do add. I just do a summation of all these states and pass that to the input. So, yeah, so just take the average of these states and then, in addition to the context maybe, or in place of the context, you can pass this to all the hidden states of the output. But this average at least solves one problem, that some information is given to the states, but different outputs may be related to different inputs. So if I am at this stage, then this is related to this word here, but I am passing it the hidden state of all the words. Right? So, and here for example, eaten is again related to this word here. So that way, it may not be a very good idea to just look at simple averaging, because at every step in the output, if I want to output this word, which is most likely corresponding to the word apple, so I want to be able to instead of looking at all the words in my context, I want to be able to focus on some words. So what do? I give a weight, right? I give a weighted average. So I look at, okay. So at time step t, I'll pass on the context C of t. At time step t in the decoder, at tth time in the decoder, I pass the context C of t, which is the sum of all the hidden contexts of the input. I is 1 to n is the length of the input, weighted by wi of t. So wi is the weight through the ith hidden state in the input, in the encoder. Now this is time dependent, this is output dependent. So I can give different weights to different states and I add them up and then I pass them to decoder. So how does this work? So let's say I ate an apple, I have this hidden state H0, H1, H2, H3. I get the first set of weights C0, which is Wi0, the first context, C0 is the first context, and it's Wi0 times Hi, and I sum it and take the average here, and I feed this to my first hidden state, right? To create my first hidden state in the output, in the decoder. Next time, I look at C1, which is a different set of weights, Wi1, different set of weights I do. And then I add these hidden states in those proportions, in the new weights, and then I feed it to the next step in the decoder. Plus, I of course take the previous output, I also take the previous hidden state of the decoder to compute the next hidden state. And so on. So I keep doing that. In general, at every time step t in the decoder, my state, the context that I pass is wit hi summation over all the hidden states. Summation over all the tokens in the input. So far so good. Now, how do I decide what should wits be? Right? So now I have the possibility that once you are looking at the apple as an output here, then you can possibly focus or give attention to this particular weight, this particular hidden state more, and then come up with a translation, right? So the network could just learn one word by word translation or whatever. So that possibility I have enabled by using these weights. But now, how do I set these weights? Huh?
I was thinking that, we can learn them, but we again fall into same issue of variable length states. If we make an ANN, like how many inputs there will be, because
No, but we can learn these weights, fine, let's learn these weights. But so what should be the inputs? My output of that machine or whatever machinery I use, whatever network I use to learn these weights, would be the weight itself, right?
But for input, how many?
Now this weight depends on I and it depends on T, right? So I'm going to use the same machinery to give WIT. It just give it different inputs, right? So one of the input could correspond to I and the other input could correspond to T. And using this I get WIT. So, so how should WIT? Yes?
Depending difference between I and T, and when there is less difference, we get more weightage to that edge length. And we exponentially due to as the difference increases.
Yes. So how do I decide WIT? Like how do I learn WIT?
The output token could be the input for this.
Okay. So let's say WIT is some function, right? Now what is it a function of?
Output at time t minus 1.
Output at time t minus 1. So which is, let's say, y of t minus 1. Okay. What else? So what have I outputted previously? I can take that as the input. What else? Huh? Which hidden state? Decoder's hidden state. Let's represent it as C of which one? What time step? previous, right? T minus 1. Okay, decoder hidden state and
The entire context vector.
the entire context vector. Okay, you can give that. You have to make it dependent on the input word also, Wi. And how do I make it dependent on W input word? Huh? You can make it dependent on WHI. Right? The hidden state of the encoder at ith time step. Now I don't have that problem, right? You are saying that you learn through the same, because now I have encapsulated I and T as the input to my network. Now the same network I have to learn somehow, and then I'll get WIT. So that's the basic idea of attention. Right? So yeah, if you want to produce this word, we want to focus on that word. How do we generate these weights? Attention weights are just the sum of these weights. And if the model is trained, it will pick up the correct weights. But how to compute these weights? And the basic idea here is that, WIT is some function of HI and ST minus 1. Just the two hidden states of the encoder and the decoder. That is enough, at least, to start with, to produce this one. These weights must also be positive and they should add to 1. Because, there's input context length or, input sentence. You want to just make sure that just add to 1 so that you can just focus on one word at a time. Or if you want to look at the whole sentence, you can give equal weightages. The model can give equal weightages. So how do we do this? How do we make sure that happens? Okay, you can focus on this formula out here. So we do it in two-step process. So EIT is a function G of HI and ST minus 1. So we said that, weights we want to, and it's the same thing except that I'm using a different symbol here. And now to make my weights add to 1, it is EXP of EIT divided by summation over J, which is over the input sentence, right? Input tokens. EXP EJT. So this will make sure that my weights at every time step T in the output, if I look at all the tokens in the input, the weights will add to 1. So this will adjust the weights to add to 1, and then these weights I can pick. Using these weights I can give importance to the particular context or particular hidden state in the input at time T. Right? So that's the key idea of these architectures. Attention.
Sir,
Yeah.
how does this depend on time?
Right? So it is the previous state of the decoder. We are just feeding that. Okay? And then the rest of it is something very similar. So this is the classic paper by Badhanu et al. On language translation. This is I think 2014 or 2016. And they were doing this RNNs, machine translation. So before that, machine translation was happening using statistical methods. So people will build statistical model and try to translate. Neural network was not used for machine translation. They started getting used when RNNs and LSTM and GRUs came up. People started using that. They were not as good as machine translations. And then this attention idea was introduced. And with some more ideas like word embeddings and all, they started behaving at par with the machine translations. But then this classical paper that came in, which says that attention is all you need. So you don't need RNNs. You just look at the input, and just by using the attention mechanisms, you could actually produce good translations. So we'll try to cover that paper. This is also a very good paper to read, so I'll make it a mandatory reading. It's a very simple paper to read. And you don't have to look at the results, just focus on the mathematics, the equations that they have done. It's not difficult to understand at all. And it's essentially the same thing that I'm talking about here. Okay? So, yeah. Now what is this function G? Right? So far I've talked about, how to make it dependent on the input context and the output time step. So that we have done. But what can the function G be now? Any ideas? Any suggestions? Dot product, yes. Well, the context may not be of the same length. HI and SI may not be of the same length. So if they are of the same length, I can do a dot product. Otherwise, I can sandwich a matrix in between that will match the dimensions and do the product. That is one. What else? Huh?
Can we concatenate the
It has to be a number here, no? EIT is a number, is a scalar. Because that's how we'll get these weights to be, adding to 1 and all of that.
ANN should also work.
Huh?
ANN should also work.
ANN should also work, yes. So here are like 2 or 3 ideas. One is definitely what you talked about, just dot product. But if they are not of the same dimension, we can sandwich a matrix in between. Or you can take a matrix and concatenate both the vectors and create a new hidden state, apply tan H. So this is basically a neural network. And then transpose times VG. So this is a single layer neural network. Or you can do a multi-layer perceptron. You can even learn a multi-layer perceptron that is going to get these weights. And that's how you get your output. Okay. Now, this looks all intuitive, and it sort of looks, that's the right thing to do, but there's something here that is going on, and I'd like to draw your attention to that. And there's one way this is fundamentally different from the neural network that we have covered so far. Either it's a convolution neural network, or it's a deep network, or if it's a recurrent neural network, or LSTMs and GRUs. There's a very fundamental difference here in the attention mechanism. Maybe not in the GRUs, I have to look at GRU more carefully, but at least in CNNs and deep networks and all of that. There's a very, fundamental difference. And can you pinpoint that? So if you look at a network, right, you have input, right? So these are your XIs, and then you have a weight, and this gives you an output, AI. What is the notation you use? AIs or ZIs? ZIs, okay. So we have the output ZIs, first layer, and then you have again weights at the second layer, and you get ZIs at the second layer, and so on. That's a typical network, neural network structure. These weights are our model parameters. And these Xis and Zis, Xis are the input, Zis are the features that I derive from the input after doing all this, multiplying with the weights, doing all this, transformations. But they are dependent on the input only. And these weights are independent of the input. Right? I learn this based on the input, but for a fixed model, I have a fixed set of weights. They don't depend on the input. Right? So at every step, I multiply the weights with the feature of the input, I get the next output. Then I again look at new set of weights, multiply, I get the new output. Now here what is happening in the attention? Again, I'm multiplying by these weights. These are the inputs. So this is my input, which is encoded in a word2vec or some kind of word embeddings, which is again I can think of it as a matrix product, right? So multiplying with some weights. Then some hidden state is computed, which is again multiplying with some weights. I have the percolation of these states. So the next state is again a function of the previous states, multiplied by the weights, I get the next state. So all of that is in the same structure, except for this step, where these weights themselves are dependent on the input. So this WIT is also dependent on the input, and HI is a state which is dependent on the input. So I'm looking at these weights which are, instead of now being constant, they are input dependent. And of course, if you think of an MLP here, then MLP will have its own set of weights which will get trained. But here in the attention mechanism, my input or the features that I created from the input, the context that I created from the input is getting multiplied with another feature that I created from the input. And then I'm getting my output, right? So what does it imply in terms of gradient backpropagation? So if I think of it just as a simple neural network in the language of simple neural networks, I have these features Xij's, and I'm multiplying it the weights to get Zij's. But I can do some feature engineering, right? Machine learning, you would have learned feature engineering. I can create quadratic features. I can look at Xij times Xij prime. Right? That's how I can create quadratic features. Or I can look at this zij's and I can also multiply it with other zij's. I can create these quadratic kind of features, which is not there in general neural networks. I always multiply the weights to get the next level of features, but nothing stops me from actually doing that. Now if I do that, how do I backpropagate my gradient? Let's say I have xi1 times x, so my function of xi is, let's say, xi1 is some g of xi, w1, some weight matrix, and again xi. Right? So xi is a vector in dimensional space, weight is a matrix, again some m into n or whatever dimensional space, and I'm giving another input as that. Right? I can do the same thing, chain rule for vector differentiation. I can differentiate with respect to the first variable, find the gradient, differentiate with respect to weight, also differentiate with respect to the third set of variables. Nothing changes. Because I still do not have a feedback loop. My output is not feeding back to my input. So if I look at the computational graph from the input to the output, it is still what is called a directed acyclic graph. Even though there are multiple paths and they are getting combined and then again they are getting, right? So two features, vectors I create, they get multiplied and then get me the output. But essentially I do not have a cycle yet in my computational graph. If I do not have a cycle in my computational graph, I can still apply the chain rule for vector derivatives. And everything else, the machinery that I have built so far for learning neural network, that is still valid. So this is an important point, you have to think about it. So so this is what I have just mentioned here. Generally, weights are learnable parameters multiplied by input or feature vectors to create the next layer of features. But here attention weights are dependent on the input, and these weights also multiply with the input features. So that's how the attention is sort of fundamentally different from neural networks. Instead of a simple computational graph, I'm creating a directed acyclic computational graph. But now, you have this idea in front of you. Now, why do you have to do this multiplication in that particular way? Can you come up? People have done, made transformers, right? Made variant transformers, and they're outperforming all the other existing models in the neural network. They are the state of the art. We are going to cover that, in the subsequent lectures. But why do you have to follow exactly that architecture? Right? So if the fundamental idea is just, multiple paths to the output where the input are getting multiplied, you can also think of, right now it's quadratic features, but you can also do, 3 level, power 3, power 4 kind of a features. So can you combine these inputs in other network in a way that it's still a directed acyclic graph, your computation, but it is much more richer. And that could lead to maybe breakthroughs in the architecture of the neural networks, beyond transformers. So there's something to think about. It's a very high level idea at an intuitive level, but one has to actually make it work at an engineering level to actually, get it to this one. So I'll stop here. Thank you. This was a very important lecture. Thanks for your attention. And so we'll continue. Yes?
You are again, I was not able to.
You're not able to.